So now we have the last talk of this session, and we are going back to engineering again. The talk is by Robin Degraeve on exploiting electronic device physics for building neuromorphic computing elements.
Thank you for the introduction, and thank you also for inviting me to the organizing committee. So I will be talking about using device physics for neuromorphic computing elements. I'd like to emphasize, first of all, that this is a kind of a personal journey. At IMEC in Leuven, where I work, there have been a lot of efforts on making machine learning hardware. Most of them actually focus on making devices that facilitate or accelerate mainstream algorithms. But I took actually the neuromorphic route, and I tried to see what can we learn from biological examples. So what I will show you here is some engineering opportunities that follow from, let's say, the intrinsic learning properties of electronic devices. And I will show you two examples, resistive RAM, but not as a weight storage element. I will use it in a different way. And I will talk a bit about the alternative use of a transistor. So let me kick this off by showing you this picture. This is the Graf Zeppelin. It's an airship. It was built in 1928. It was actually a very successful thing because it could do transatlantic crossings. It was flying from Germany to the US or from Germany later to Brazil. It could take about 50 people. Half of them were crew members. And it was actually, airships in general had a perfect safety record until 1936. And if I show you the competition, 1927, this is the Spirit of St. Louis. It could also do a transatlantic crossing. It was actually the plane that did the first transatlantic crossing with one person aboard, be it a very courageous and also very lucky pilot. And airplanes at that moment had a terrible safety record. So, what technology is the best one now? Well, at that moment, airplane technology was already more than 20 years under development and research. And still, in a benchmark, if you would do a kind of management-style benchmark, on many criteria, this could not compete with the other technology yet. Now, I'm pretty certain that none of you here came to this conference by airship. Okay. So what was the reason why the airplane actually won? Well, it had more potential. And I think recognizing potential performance at a certain moment is much more important than evaluating the present status. So let me continue a little bit on this aircraft example. What can we learn from biological examples? Learning to fly is from a biological example, like this bird here. And you can do two things. You can actually say, do I have to copy the details of this biological example, the structure of the feathers, or do I have to investigate how the wings should be flapped? And then you will reach this kind of machine, which was actually patented in 1889. Or do I have to look at a more conceptual level? Like, look, this bird uses the principle of aerodynamic lift, and it has a method of propulsion, and it has a method of navigation. And then go to a technological implementation of those concepts, and then create an airplane. And you might not agree what you want to put as concepts there. So if, for instance, if you leave out the aerodynamic lift and you say, I can replace that by some other mechanism that can also lift me in the air, well, then you end up with your airship, which is also a good solution. It's just that it is not the solution that we targeted for the specific application that we were building these things for. Okay, so let me now look back to the topic of this conference. What can we learn from our biological example? So you can ask the same questions. Do we have to copy the chemistry of a synaptic conduction, or maybe the organization of the brain? To what level do we have to copy that? Is the network of neurons and synapses, is that a crucial thing in making an artificial intelligence? So should we copy actually the action potentials? I think if you do that, you will end up with an artificial brain, which is very interesting. But maybe we should look a bit at more conceptual level. Like, how does the brain learn and generalize? The brain is a model builder that tries to explain observations. I think we've just seen a very nice talk about that one. It uses distributed, context-aware storage and representations of data. And computer memory are completely merged. And if you take these concepts and then you go through a technological implementation of them, you end up with an artificial intelligence, which is not the same as an artificial brain. Now, I'm sitting here in this room, so depending on whom you ask, there will be a lot of discussion on which concept, what you should put in what column. Maybe some people say, yeah, the use of action potentials is very important, so we have to go to spiking. That's a conceptual thing, has to move to the right. So we can discuss about that. This is just a choice that I've made here. But take, for example, the network approach. I mean, how essential is it? I've taken the liberty of making a very small schematic drawing here of my own network, which consists of nodes. You can call them neurons if you like. And connections, you can call them synaptic connections if you like. The first thing you can do is you can organize them in layers and make sure that all the arrows point in the same direction. And then you can clearly define an input and an output. And we have training methods for that. And these are very suited things for static data. They can be trained by mathematical methods. We like that because that gives us the control on what we are doing. But we need very large data sets, and it's pretty slow. If we have data which is not so static, but for instance, which needs context information, or which evolves as a function of time, needs time awareness, we need some feedback loops. So we go to recurrent networks, STM, and you can still train that, but it gets even harder. This is actually you can make very large networks like this. They're very difficult to train with a lot of data. For me, these are the airships of the AI. They can do wonderful things. They can cross the Atlantic in a matter of speech, but in a very inefficient way. Now, let me go back to my network. What if you say, I don't care about all these connections, as long as this network is sufficiently dynamic and sufficiently complex? So I just call it a reservoir then, and I still have to define somehow an input and an output, and that's the only thing I care about. And training, well, as I said, we don't care about the connections, so we don't do the training. The only thing we do is a little bit of training at the output, which basically means that I have a scrambled brain, and it does something for me, and I try to make sense of what it does. Now, if you don't care about that network, why make it? You can just replace it by a physical system that can actually do the same function for you. At that moment, we're talking about physical reservoir computing, and at that moment you just moved the conceptual idea of having a network from the right-hand column to the left-hand column, because this is done not by a network that you actually implement, it's a physical system. Now, this is an important part because this opens a lot of opportunities for engineers, because a lot of devices, and I'm an electronic engineer, a lot of electronic devices are actually physical systems, and they are very complex usually and very dynamic. So they can serve as these reservoirs. But you have to give away the control. Usually you don't know what these physical systems are exactly doing because it's at an atomistic scale inside the device. And that is sometimes a hurdle that some engineers cannot take. But I think you have to take them. Now, if you really don't want to have a physical system there, you can also put a mathematical construct there. You can just design, basically, your representation of your input in a higher dimensional space, because that's what that reservoir is finally doing. And you can take random vectors, then you're in the field of hyperdimensional computing, or you can just design your code yourself, make it context sensitive, make it sparse, and make it bio-inspired. Now, one further note on learning. I think learning is much more than just parameter training. I mean, we just had a very beautiful talk that illustrates this picture. Our brain is building models, is constantly predicting and checking them with perception, and when there is some modification needed, it feeds back and it changes the hypothesis. And we also have mathematical methods to do that. The simplest one goes back to 1763, Thomas Bayes, who actually introduced this Bayesian inference techniques. Okay, that was a very long introduction from my part. So let me first introduce myself now. So as I said, I work at IMEC. I work in device reliability. So for 30 years already, I'm modeling the failure and degradation of electronic devices, be it mainstream devices, as well as novel technologies. So you could wonder, what does device reliability have to do with neuromorphic computing? Now, it's quite simple. If you want to understand the reliability of a device, you must understand its operation in very great detail, often to the atomistic detail. So, because a lot of defects in materials are the reason why the devices fail. But exactly these defects create these very interesting dynamic processes that you can use for learning. So many electronic devices are actually physical systems with complex behavior. A transistor is usually used as a simple switch, but it's actually much more complicated than that, and you can do a lot. You can do other things with that, also with that transistor, also, as I will show you in a moment. Many devices actually have very interesting properties that can be learning properties, and the only thing you have to do is you have to harvest those properties. So this is a total bottom-up approach that I took. So top-down means, for me, that people have designed algorithms, and you try to make hardware, you try to make devices that can implement that algorithm as efficiently as possible. What I did is exactly the opposite. I start from the device, study the device properties, and from those properties try to build up a learning system that exploits or harvests exactly those physical properties. That means that I will be focusing mostly on very small scale. I'm not going to show you a natural language processing model, no. It's going to be very small scale, specific applications, very low power, because I really use those specific properties of individual devices. In other words, it's very useful to implement in the edge, like on your mobile phone. The first device that I would like to introduce is resistive RAM. You have seen it already a few times in this conference. Basically, it's a filament of defects that can be manipulated. So I'm going to specifically talk about oxygen vacancy-induced resistive RAM. We have basically a top electrode, then what we call an oxygen exchange layer, and a bottom electrode. And from the oxygen exchange layer, you can actually grow a conductive filament to the bottom electrode. Now, if you apply a negative voltage to the top electrode, you can actually shrink, make that filament narrower, and it will conduct less current. If you apply a positive voltage, you will make it wider again. It will actually conduct more current. If you push it further, give it more negative voltage, you can even break the filament, interrupt it. And if you apply a set voltage, positive voltage, you can reverse it again and recreate it. Now, in most papers, the picture in the middle there is considered as the high conductance, and the interrupted filament is considered as the low conductance, while I think most people in reality use this. They are just modulating the size of the filament without ever breaking it, and there's a lot of experimental evidence for that. So the standard uses like high voltages. They use it as a switch, as a memory device to store information with, for instance, a set voltage of 1.5 and a reset voltage of minus 1.5. And people are wondering, can this store weights? So they actually try to have intermediate states. I'm not going to do that. I'm going to use it in an alternative way. I'm going to use it as a stochastic device where the set voltage is 1.5, that doesn't change, but the reset voltage is much lower. It's like a soft reset with only minus 0.8 volts. And then you can observe some very interesting properties. So if you apply one set pulse, you form this filament. It's in a high conductive state. But if you apply it on a soft reset, you have some probability of resetting it, of making it a low conductive device. And the probability of doing that is actually very high. It's still efficient. Although the voltage is low, minus 0.8, you can still efficiently reset this device. However, if you apply more than one set pulse, the conductivity of the resulting device in a high conductive state is actually not that much different. But if you now try to reset it, it's going to have a low reset probability. So it's like the filament got stronger. It's more resilient against this soft reset. And you can nicely show that. This is the data on OxRAM devices for two different current conditions. So on the bottom axis, you have the number of set pulses. And on the left-hand axis here is the probability for reset. And you can see that if you only have a few set pulses here, your reset probability is high, but it very quickly drops as you have more set pulses. And the red line on the top here corresponds to the right-hand axis, which is actually the resistivity of the filament, and it doesn't change that much. So you cannot really see a different conductivity level there. So how can we use this property, try to harvest this property? Well, what we did is we tried to build a time series learning system using an RM crossbar. So we have here a time-dependent signal. We took a database which comes from a gait. So a person walking around a certain trajectory here, and he's wearing a waist belt with an accelerometer, and that gives us a signal of a few seconds. In this case, it's the y component of the angular velocity. On the other hand, we have a crossbar array. A crossbar array, that means at every cross point, we have this resistive memory, the RME, the resistive memory element, in combination with the transistor that actually limits the current and that allows us to select those devices. So how can we now use that property of that resistive RAM, the stochastic property of the resistive RAM, to learn that time sequence? Well, we can try to, at the, let's say, the horizontal lines, we will feed in the data at the time t, and we'll try to make it a predictive model, like a brain is a predictive model, to predict the time to predict the data at time t plus tau, a certain delay. So let's do that. So we take the input here. This is activate this line, and here's a physical connection. So it's not a weight, it's just a physical connection, either a 0 or a 1. It's a connection or no connection to that predicted data. Now, obviously, the same data appears somewhere else and has a different prediction. So how do you discriminate between those two predictions? In order to discriminate, you need a code. You can actually try to describe the information not by a single input line, not by a single neuron, if you like, but by a combination of neurons. So think, for instance, of the olfactory receptors. We only have like 300 receptors in our nose, but we can that can detect different molecules. Yet we can detect thousands of different odors because we have actually a combinational detection system. So, for example, if you only have 10 neurons, a group of 10, and you activate 3 of them, 3 out of 10 is a combination, and there are like 120 possible different combinations, also already with only 10 neurons. So let's do that. And so instead of having this data related to one line, we have it related to a group of lines, and we have a combination active of them. And that combination predicts another combination at t plus tau. With this in place, you can now build the following learning algorithm, or training algorithm. So at each moment in time, you have the data at the time t. You do a prediction. That means you read out which connections are already there. That gives you this prediction. Then you look at the data at t plus tau. The ones that are correctly predicted, you give a set pulse, which means you actually strengthen those connectors. The other ones, you give this soft reset pulse, which means that you give them a probability of actually shrinking the connection. And if you run that, and we actually did that on real hardware, so we have our 1 megabit chip here, which we only used a very small fraction of that chip, actually. So it's a crossbar array with with tantalum oxide-based filamentary RM. We have some control software around it, mounted it on the rack, and actually we did the whole this algorithm that I just showed you. We run it on this gate data, and then this time sequence is translated into a network of connections on that crossbar array. This is done with only one pass of only 600 data points. So every number corresponds to a group of neurons, and the individual dots are the individual connectors inside that group. So how good is this model now? How can we test this model? Well, what you can do is you can go for instance, an authentication task. So you can do training of one subject's data that gives you this model for that subject. And then you can verify, for example, if you have a test subject, how well does the data of the test subject, how well is it predicted by this model? So you construct some kind of matching score, and we have here a cumulative distribution, and each time we present data from the same person as the training, we write down the score in this distribution, which hopefully is a high score. And if the test and the training person is not the same, we have a separate distribution which we plot actually inverted. And hopefully that's a much lower score. So ideally, these two distributions should be completely separate, and then you can authenticate this person just by the way he walks. Ideally, in reality, they are always a little bit overlapping, unfortunately, and the cross-section here is the equal error rate, which is typically the measure that is taken to quantify the goodness of these networks. So on our system, with one pass of the data, we get like 13%, which is not impressively good, but it's also certainly not bad, because we only used 600 data points, and we only passed that data once. And that already builds us a nice model, just using this local learning rule that is built into this filamentary resistive RAM. Can we do better? Sure. We can look at a very interesting device that we all know, which is just a transistor. A transistor has a reliability problem, which is called bias temperature instability. We have been looking at that problem already for 25 years in our research group. We understand it very well. We have nice models for it, physical models for it. We have compact models for it. We know how we can calibrate it also on different technologies. We know how it works. We always try to get rid of it. So I'm going to show you here how you can actually use it. So what is it? If you have a transistor, in the gate oxide of the transistor, there are always a number of defects, a number of imperfections that are intrinsically there. Now, if you have a channel formed from source to drain, these carriers can actually be captured in those defects, and when the channel is not there, they can actually discharge again. So that's all it is. But, so if you see what's going on, for instance, this is a simulation using our physical model. What this does is, if you have discharge in the oxide, the threshold voltage of the transistor will shift. So for instance, if you give it a number of pulses at the gate, you will see that the threshold voltage shifts because of discharging of that oxide. And if you remove those pulses, they start to discharge again. Now, bias temperature instability, since there are many defects, has a very broad range of time constants, from very short time constants, nanoseconds, to even months. So you can actually measure any time with that system. And we have plenty of transistors, of course, available, so why not use this? So how are we going to do that? Let's go back to our time series. This is a time series that's again from gate data. It's actually the Z component this time. And we're going to move in the same direction. So we're going to plot the data versus a delayed version of itself. But instead of predicting the data, we're just going to plot that data. So that means you're always going to plot the data at t versus the data at t minus tau. And that creates this trajectory in this plot here. This is called two-dimensional phase space reconstruction. I mean, mathematicians know this very well. You can do this in 2 dimensions. You can do it in 3 dimensions, higher dimensions also. So we write this trajectory. And then we quantize in a number of bins the data and the corresponding phase space space. And we make sure that in every bin we have on average, on a large number of data, we have on average the same amount of information. If you now replot this trajectory as on a scale of bins, it looks like this. Okay. What we'll now do is, with each bin, we associate one transistor. And when we are writing this trajectory, as you can see here, each time we move through one coordinate in this phase space, we give a pulse to the corresponding transistor. So if you look at the full system, it looks like this. We have our data. We divide it in a number of bins, which are equal in density, information density. We do phase-space reconstruction. All these coordinates here correspond to one device, and each time the trajectory passes through one of those coordinates, you give a pulse to the corresponding transistor. So it goes here to the transistor. And the transistor will respond to that through that bias temperature instability effect. You can read the outcome of that at regular intervals, and you can just take the sum of all those outcomes and construct this vector, which is like a fingerprint of your data. Note that this is actually a form of spiking neural nets, but it's in a completely different way generated because it's really the order and the timing of the spikes which controls the information and which is also driving these transistors. And these transistors are actually small reservoir computers. This is the real data. Note that we only took 3 bins, so this is like a 3x3 system with 9 transistors, really very small scale. And this is the actual response of the transistor on this time sequence here, creating a vector. So there's a lot of stochasticity. I mean, it's not always a completely reproducible signal that you get, but that doesn't matter. We just take the measured values. And if you look at equal error rates that we obtain with that, well, there is a dependence on the size of the transistor, but we see we are down in the 8 to 5% with just 9 transistors. That's all we used. So we have this complex time signal from person walking, 5 seconds of data. We pass that data once through the system. Yes. The system has only 9 transistors, and we can already authenticate these persons with very high accuracy. So, in summary, I've tried to advocate to you a kind of bottom-up approach where from the physics of a device, we actually build a learning system. Making neuromorphic computational elements that behave exactly as you want them is not easily achievable. So we don't do that. I don't do that. I try to use many existing mainstream or novel electronic devices that have often undesired properties, and I try to use those properties to make neuromorphic elements. To do that, I have to harvest these properties and build biologically inspired, but not copied, systems. And with that, I'm going to close my talk. Thank you.
Thank you very much, Robin, for this new perspective. We have time for questions. Yes, please, on the right.
Thank you very much for the nice talk. So my name is Ahmet from TU Dresden. I would like to ask if you use a standard transistor or is the gate modified, the oxide is modified?
It's just ordered at the foundry, so it's a very standard transistor.
Okay, thank you very much.
Hi, I'm Sebastian from Forschungszentrum Jülich. So my question would be, in your first system, how do you cope with real time at all? And in the second system, is there a way to also include time warping or like a changing time constants?
Yeah, there are 2 options that you have. You can do it real time, or you can say I store the data and I process it at a kind of clock frequency that you would typically do in a digital chip. Of course, so for the first system that I've shown with the resistive RAM, it doesn't really matter because you need the pulses, of course, and whether you give them with real-time intervals or not, it's a non-volatile memory, so it will just remember its state. That's not going to influence it. For the BTI, of course, these are time constants, which so the system evolves as a function of time. So that is very important, whether you take it at a fixed frequency or you take it at a real-time frequency. At this moment, we actually just implement a single device, and we actually give the pulse train at a certain fixed frequency. But yeah, we are looking at into that, what would be the best option, and how can you actually take the best of that device. Yeah.
Thanks.
Mm-hmm.
Thank you. Yes, please.
Thank you very much. Could you turn to the slide 18? Because I'm very curious about the way you train the device.
18,
so,
that's far back.
Yeah, the small set operations. it seems that you use more set operations to strengthen the filament, right?
Yes.
So did you already check the difference between higher voltage set process, the influence of higher voltage set process on the configuration of filament? Yep. Is there any difference between more set cycles and higher set voltage?
Yeah, there is a difference between the ratio between the set voltage and the reset voltage is actually controlling that. And also the compliance level at which you're so controlled by the current compliance is actually also influencing that. So I think it's not in the presentation, but in the papers you can find pictures with different voltages and different sets. So they actually control on what scale this drop happens, on what, yeah, clearly. There's a clear dependence, yes.
Okay, thank you very much.
First question in the back, and then last question in front.
Yeah. I'm Degraeve from Aachen University. Very nice presentation. You presented this bottom-up approach. On the other hand, you give an example like 9 transistors and they have a certain accuracy. How do I know what kind of system I would build if I want to have a certain accuracy? Don't you need like a top-down model or algorithm to know how to build this system?
Well, especially the system with the transistor is actually quite generic. So of course, there are some methods to process, in fact, they can process any time sequence data. But of course, the resolution, the number of bins that you need, the time constants can be different. But that can be adapted. I mean, there is no reason why you should use a different system for that. So if you want to reach a certain accuracy or a certain functionality, there are mathematical methods to calculate, for instance, the hyperparameters of the system, which are like the delay time, the number of bins that gives you the resolution, basically. So there are some methods that we have already investigated to do that. As I say, in general, you can process any time sequence, but you need the versatility to have a certain size of that crossbar of that array, actually.
Okay, thanks.
Hi, thank you. Elisabetta from 1Qubit. I was curious about the fingerprint you create of data. Is that invertible, or the transistors increase the noise, so it's not possible to recreate the original data? Let's say, how much is the accuracy you can have on the original data?
As I said, there's not a predictive model, so I have not even thought about how to invert that. I mean, these transistors behave in a very stochastic, nonlinear way, so I don't think it's going to be very easy to invert that system.
I was thinking, how is explicable the model you create, like the the model you create when you distinguish between people, if you can connect the prediction that you make on the original data. Yeah, but we're talking about the RM system now, or the transistor system, because the RM system, of course, is a predictive model. You can always predict the outcome of the data at a certain interval in time, starting from the data at the time t, so you can always match if the prediction is corresponding with the actual observation. That's actually how this matching score is calculated. But after you introduce this transistor, you increase the score.
But in principle, if you have this model, you can always generate a prediction, the most optimal prediction, and use that prediction as input again, and recreate the data in that way. So it's really a model that can recreate the data for the resistive RAM. For the transistors, that's not going to work, I think, because there is a nonlinear transformation inside the transistor that's not going to be reversible.
Okay, so let's say after you introduce the transistor, what are you losing? Like I was surprised. It was nice to see how the prediction improves. But
the accuracy improves.
The accuracy
but
improves,
the prediction is you abandon actually the prediction. Okay, let's take this up maybe after the talk.
Thanks a lot for trying to clarify this. So let's thank Robin again.